Distributed systems from scratch. This is episode 5, consistency models. Last episode we learned the CAP theorem says you must choose between consistency and availability during a partition, but we used consistency as a single word as if it means one thing. It doesn't. There's an entire hierarchy of consistency models, from the strongest guarantee you can make to almost no guarantee at all. And understanding this hierarchy is essential for designing distributed systems. In episode 4, we saw that CAP's C means linearizability, the strongest model. But we also said consistency is a spectrum. Today we walk that spectrum. We will start at the top, linearizability, and descend through sequential consistency, causal consistency, and eventual consistency. At each level, I'll show you what guarantees you get, what anomalies you're exposed to, and which real systems use it. By the end, you'll know exactly which model to pick for any piece of data in your system. Here's the spectrum again. On the left, eventual consistency, weakest guarantees but cheapest and most available. On the right, linearizability, strongest guarantees but expensive and unavailable during partitions. Think of each model as a contract between the system and the developer. A stronger contract gives you more guarantees to rely on, but costs the system more to uphold. In latency, in coordination, in availability. Let's start at the top. Linearizability, the gold standard, the strongest consistency model in distributed systems. Linearizability means every operation appears to take effect instantaneously at some point between its invocation and its response. Let me unpack that. When you send a write request at some moment during the time between when you sent it and when you got the response, the write happens. And once it happens, every subsequent read from any node, anywhere, sees that write. The system behaves as if there's a single copy of the data. Even though there are many replicas across many machines, from the client's perspective, it looks like one machine with one copy. If client 1 writes x equals 5 and gets a confirmation, and then client 2 reads x, even from a different node, client 2 must see 5, not 3, not null, 5 or an error. This is sometimes called the single copy illusion. Here's the visual. Time flows left to right. Client 1 performs a write of x equals 5. Somewhere during that operation, at the linearization point, the write takes effect. Any read that starts after the write completes must return 5. Returning the old value 3 is forbidden. It would violate linearizability. Systems like Google Spanner, CockroachDB, etcd, and Zookeeper provide linearizability, but it's expensive. It requires coordination between nodes, which means higher latency. Spanner literally uses GPS clocks and atomic clocks to make this work across continents. One step down, sequential consistency, the guarantee. All nodes see operations in the same order, and that order respects each client's program order. But unlike linearizability, the global order doesn't have to match real-time wall clock order. Here's what that means. Client 1 writes x equals 1, then y equals 2. Client 2 writes x equals 3, then y equals 4. Under sequential consistency, all nodes will agree on some interleaving of these operations, but the interleaving doesn't have to match the actual wall clock times. Maybe everyone sees x equals 3 first, then x equals 1. That's fine, as long as within each client's operations, the order is preserved. This is weaker than linearizability because two operations that happened at different real-world times might appear in reverse order, but all nodes at least agree on what that order is. The difference in a nutshell. Linearizability is like a single-threaded program. Everything happens in exactly the order it appears to happen in real time. Sequential consistency is like a multi-threaded program with a global lock. There's a consistent ordering, but it might not match wall clock time. Sequential consistency is cheaper because nodes don't need to synchronize with real time. They just need to agree on a total order. This is already much easier. Now we reach what many consider the sweet spot of the consistency hierarchy: causal consistency. Causal consistency guarantees that operations which are causally related are seen in the same order by all nodes. But operations that are concurrent, causally independent, can be seen in different orders by different nodes. Remember what happens before relation from episode 3? This is where it becomes practical. If event A caused event B, because A sent a message that B received, or because they happened sequentially on the same node, then every node sees A before B. But if A and B are concurrent, no information flowed between them. Different nodes might see them in different orders. And that's fine, because there's no correct order for causally independent events. Think of a social media feed. Alice posts, "Who wants coffee?" Bob sees it and replies, "I do." Bob's reply is causally dependent on Alice's post. Without causal consistency, you can get absurd results. Alice posts, "Who wants coffee?" Bob sees it and replies, "I do." Now Carol opens her feed, but Carol's replica received Bob's reply before Alice's post. Carol's feed shows Bob says, "I do," followed by Alice asking, "Who wants coffee?" The reply appears before the question. It's nonsensical. Carol has no context for Bob's message. Causal consistency prevents this. Because Bob's reply is causally dependent on Alice's post, the system guarantees that Alice's post appears first for everyone. Always. Here's why causal consistency is so important. It's the strongest consistency model that can be achieved while maintaining full availability during network partitions. Linearizability and sequential consistency both require coordination. Nodes need to communicate to agree on an order. During a partition, that coordination is impossible, so they sacrifice availability. Causal consistency tracks causality using vector clocks, the mechanism we learned in episode 3, and vector clocks don't require any coordination. Each node can independently determine the causal order based on the information it has. This makes causal consistency the strongest AP-compatible model. It's as good as you can get while still saying yes to every request, even during a partition. At the bottom of the hierarchy, eventual consistency, the weakest useful model, but don't underestimate it. It's probably the most widely deployed consistency model on the planet. Eventual consistency makes one promise: if no new writes occur, all replicas will eventually converge to the same value. That's it. No ordering guarantees, no real-time guarantees. Reads can return any previously written value, including values that were written a long time ago. The word "eventually" is deliberately vague. It could mean milliseconds. It could mean hours. Here's a timeline. At t equals 0, you write x equals 5 to node A. At t equals 1, you read x from node B and get 3, stale, but valid under eventual consistency. At t equals 2, node B has received the update, you get 5. But at t equals 3, node C still hasn't received it. That's also valid. It'll get there. Eventually. This weakness leads to real anomalies that can confuse users. Stale reads: you update your profile photo, you refresh the page, but your request hits a different replica. You see the old photo, refresh again, the new one appears. Read your rights violation, you post a comment. The page reloads, hitting a different replica. Your comment isn't there. You panic, thinking it was lost. It wasn't, it just hasn't propagated yet. Monotonic read violation. You see 10 likes on a post. Refresh. 8 likes. Time appears to go backwards. Refresh again. 10 likes. You happen to hit a more up-to-date replica than a less up-to-date one. These anomalies are confusing and annoying even if they are technically correct under the consistency model. The solution is to bolt session guarantees onto eventual consistency. These are weaker than causal consistency but much stronger than bare eventual consistency. Read your writes. After you write a value, your own subsequent reads always see that write. You won't lose your own comment. This is typically implemented by sticky sessions, routing your request to the same replica. Monotonic reads. If you read version 10, you will never subsequently read version 9. Time moves forward for you, typically enforced by tracking the highest version you've seen and only accepting reads at that version or later. Monotonic writes. Your writes are applied in the order you issued them. Write A before B, always. Writes follow reads. If you read a value and then write, your write is ordered after the value you read. This prevents causality violations within a session. Most production systems that claim eventual consistency actually provide eventual consistency plus some or all of these session guarantees. It makes the experience dramatically better for the user. There's one more model worth knowing: strong eventual consistency. This adds a key guarantee on top of eventual consistency. Any two replicas that have received the same set of updates, regardless of the order they received them, are in the same state. No conflict resolution needed. No last write wins. No manual merging. The data structure itself is designed so that all orderings of the same operations produce the same result. This is the guarantee provided by CRDTs, conflict-free replicated data types. We'll dedicate a full episode to them later in the series. Strictly speaking, strong eventual consistency is a different axis from causal, not cleanly stronger or weaker, but for our purposes, think of it as eventual consistency upgraded with a convergence guarantee, achieved without any coordination. Here's the full hierarchy from strongest to weakest. At the top, linearizability, real-time ordering, single copy illusion, the most expensive. Below that, sequential consistency, global agreed order but not tied to real time. Below that, causal consistency, preserves cause and effect ordering, the strongest model that stays available during partitions. Then, strong eventual consistency. Same updates produce the same state, regardless of order. CRDTs live here. And at the bottom, eventual consistency. Converges given enough time. The cheapest and most available. Every level down trades some guarantee for more availability and lower latency. Let me put this all in one table. Linearizability, real-time, single copy behavior, sacrifices availability during partitions, highest cost, used by spanner and etctd. Sequential, global agreed order, also sacrifices availability, used by zookeeper. Causal, causal order preserved, stays available during partitions, medium cost. MongoDB supports this with causal sessions. Strong eventual, same updates give the same state, always available. React's CRDTs and AutoMerge use this. Eventual converges eventually, always available, lowest cost, used by Cassandra, DNS, and most caching systems. So how do you choose? Ask these questions about each piece of data in your system. Can a stale read cause money loss or a safety issue? Then use linearizability. Bank balances, inventory counts, distributed logs, these need the strongest guarantee. Does the user need to see causally consistent data? Then use causal consistency. Social feeds, messaging threads, collaborative documents, the user needs to see causes before effects. Is a brief stale read harmless? Then eventual consistency with session guarantees is fine. Profile data, analytics dashboards, recommendation engines, a few seconds of staleness doesn't matter. The key insight: you make this decision per operation and per data type, not once for the whole system. Here's how this looks in practice. Imagine an e-commerce platform with 4 different data domains. Payments, linearizable. A double charge is catastrophic. Use spanner or serializable isolation. Pay the latency cost. Comments, causal. A reply must appear after the parent comment for every user. Use MongoDB with causal sessions. It's cheap enough and prevents the reply before question anomaly. Recommendations, eventual. If you see slightly stale product recommendations for a few seconds, nobody cares. Use Cassandra or Redis. Shopping cart, strong eventual consistency. 2 devices add items to the cart simultaneously. Use an OR set CRDT. All ads are automatically merged without conflict. 4 pieces of data, 4 consistency models, 1 system. Let's recap. 1. Linearizability is the single copy illusion. Strongest, most expensive. Use when correctness is non-negotiable. 2. Causal consistency is the sweet spot, the strongest model that stays available during partitions. Use when cause and effect ordering matters. 3. Eventual consistency is the cheapest, but adds session guarantees. Read your writes and monotonic reads to avoid confusing anomalies. 4. Choose per operation, not per system. Different data has different needs. 5. Strong eventual consistency powered by CRDTs gives convergence without coordination. We'll cover CRDTs in depth later. In the next episode, we finally tackle consensus. How do multiple nodes agree on a single value? This is the problem that Paxos solves, the algorithm that Leslie Lamport described using the metaphor of Greek legislators on the island of Paxos. It's famously difficult to understand. Papers have been written about how hard it is to understand, but we'll break it down step by step, and by the end, you'll see the elegance behind the complexity. That's episode 5. Consistency models, from linearizability down to eventual and everything in between. Season 1 is almost complete. Next time, we enter Season 2. Core protocols starting with Paxos. Thanks for watching.